Okay, let's get started in the renewable energy session. For you, we have Dr. Fournier. He will give a talk on analysis and simulation aimed at electrical fracturing for enhanced geothermal systems. The second speaker is not here, so we can take a bit more time so be more relaxed. Please.
Thank you. What do I have, 25, 30 minutes? Or well, maybe 40 minutes, we'll see.
You can do 40 minutes.
Give me a warning when I'm like near 5 minutes or so. Let's try. Okay, thanks for being here. I'm Aimé Fournier. I'm a research scientist and principal investigator over at the Earth Resources Lab, which is in the EAPS, Earth, Atmosphere, and Planetary Sciences in the green building here. This is one of several projects I'm involved with. So this is a collaboration. I have a mouse here. Yeah, there it is. Can you? Yeah, it shows up good. I'll just do it this way. There's a collaboration with Idaho National Lab, 2 collaborators there, plus some interns, and also with Eden Geopower, which is a startup company here in Cambridge. They're actually the lead. There, Paris Smalls is the CEO there and the PI of this project. He's contracting out to us at MIT and to Idaho National Lab. This is an ARPA-E project. And that's the lead institution for that. These are all logos. So, by the way, I love being interrupted, so I'll try to keep an eye on you. And if you have any questions at all, please raise a hand or just shout out. My introduction. This is just off the Eden website. So we have this award from the DOE ARPA-E program. And the idea is to develop new technology for geothermal stimulation. This is in regard to what's called enhanced geothermal. I think you know, enhanced geothermal systems. So we want to create the fracture networks in the earth where they don't exist, so that we can have geothermal energy located where it's convenient to locate it. And you might know that fracking is very problematic because of the use of water and the induced seismicity and other concerns. So we're exploring and trying to develop technology to use electricity instead of water. So this is a somewhat fanciful illustration of that idea. The idea is you would have 2 boreholes in the earth with a cathode and anode, and you would do some small fracturing hydraulically just to sort of start the process, and then convect some conductive proppant into these fractures. And then this proppant would have a much higher conductivity than the earth formation. So then if you do a potential difference between the 2 boreholes, between the anode and cathode, then you can transmit a large electric current and create a plasma and do a lot more damage and fracturing to create a fracture network suitable for enhanced geothermal. So we've been doing this project for a few years. We're learning a lot. These are some recent publications. I'm going to give highlights from 2 of these. Mostly in this, I should say, this project has multiple components, both in the lab, at sort of the desktop scale, also developing devices at about the meter scale. And there will be a delivery in a year or so to try to do some field simulations. And most of our work has been sort of at the lab scale numerical simulation. That's what I'll mostly talk about. I'll also talk about sort of some mathematical analysis, just to understand the physical processes and try to teach ourselves what will the sort of dominant processes be. So I'll start talking about this work. This is one of our earlier publications. It's about the numerical method for having fracturing based on a pulse. So what I showed in the earlier slide was the idea that you'd have a short-term high voltage pulse of energy, which would fracture the formation, and how do we simulate that? So I'm an applied mathematician, so I like equations. I have seen some of the presentations earlier have had some equations and some haven't, so I decided to share the equations in order to sort of talk about the physical processes that are important, but I'm going to explain what everything is. So these are two equations. The first equation expresses the conservation of mass. Mass cannot be created or destroyed, it has to go somewhere. So it's expressed in terms of the pressure. So P dot is the rate of pressure change at a point. This is throughout the whole domain. The fluid compressibility, that translates the pressure change to a mass change. The permeability tensor of the rock. So if I'm flowing through the rock, the permeability decides how much flow I can really push through the rock based on the, not just the pores in the rock, but the geometry of the pores, the pathways which are allowed through the pores. The fluid viscosity, it's harder to push a more viscous fluid. Something called the Biot coefficient tensor. So this goes back to the work of Biot in the 40s and 50s. Very sensitive. So that alpha is going to couple between the pressure and the rock in which the fluid is moving. That coupling goes through this strain rate tensor. Don't worry too much about this math, but it's there in case you want to ask me any questions. And then the fluid injection rate. So that's the key thing in hydraulic fracturing is you inject the fluid, and then that fluid injection causes the pressure to increase with some other effects. The other equation is just F equals ma from your physics class. So the rock mass density is like the m. The u double dot is like the acceleration. There's a damping rate, which is proportional to this eta, and the velocity. These are the velocity of particles in the rock skeleton. They're being pushed on by the fluid. And if they're pushed on enough, we need to invoke some kind of criterion for that pressure to cause damage to the rock. I won't go into those details, but this is the basic equation. The stress tensor, so this is related to this strain tensor in the previous equation. This D is sometimes called the stiffness of the elasticity. Excuse me. This is the same alpha and P as before, so this is again the coupling between the fluid pressure and the rock. Hope it doesn't get worse. Excuse me again. And then I said F equals ma, so in some sense the acceleration terms are here. This divergence term is a kind of a force, and then we have an external force or body force. And that's what we need to learn to simulate that would come from the electricity. There'll be different physical mechanisms where the electricity applied across the boreholes will create a mechanical force and get the system going. So we're still exploring that, but we have some preliminary tests that I'll show you. You'll see the phrase Joule heating coming back during this talk as I refer to it in different ways. Okay, we're still on this paper, just to show one of the results of it. This is a snapshot of the displacement in one direction, so the x direction of displacement, which would be to the right, red or blue for positive or negative, so it's sort of dividing. And then you see there are some fractures. So the fractures are caused by a failure criterion, which is not explained in this talk, but it's in that paper. It's a finite element method, so there are nodes which are initially aligned. And then there's a criterion that says when there's enough difference in the stress along and normal to those, to an interface between these elements, then a fracture will happen. And that so-called traction and split nodes method considers some of the physical properties. So the dynamic and static friction coefficients. As the fracture opens, the rate of the fracture opening depends on the length of the slip and also the aperture, the width of the fracture. Also the tensile strength of the material of the rock formation, and then what the past damage during the simulation has occurred. That'll reduce the strength. And just for comparison, this is a qualitative comparison, of course. This is an image of an actual fracturing experiment by some other authors, and it was sort of an inspiration for this numerical experiment. The other part of the simulation I mentioned, besides fracturing, we need to transport electric propant or a propant which will be electrically conductive into the fracture. So I'm going to show some equations and explanation for that. This is the Darcy flux equation. So I have a mixture of propant and some fluid carrying the propant. And that depends on the permeability, Kf, same as different notation because it's a different paper, but basically the same K as earlier. The viscosity again, but now the viscosity of a mixture. So the viscosity will depend on the solution that I'm computing. The pressure gradient again as before, but now we're including gravity because the mixture will feel the gravity and sort of settle down, as you'll see. Another equation for the conservation of mass again, now expressed as the conservation of the mixture density. This variable C represents a combination of the different densities of the mixture and the fluid and the propant to get the concentration. And that'll be the electrically conductive propant that I need to circulate to get into the fracture so that I can do the electricity trick later on. And then there's the velocity of the propant, which when the concentration is 1, it just moves along with the mixture. But if the concentration is small, then there's some slip. And so this, in the paper, there's a long explanation of how the slip velocity is depending on the concentration. And then there's this conservation for the concentration itself. And then that involves the thickness of the aperture of this fracture that I'm solving this in. If I do some math and eliminate some variables, I get basically 2 equations and 2 unknowns for the concentration and the pressure. So to show some results from that, this is a 3D simulation. I might mention this is all using the Moose simulation framework, which is a product of the Idaho National Lab and very user-friendly and has a lot of great capabilities. So I want to advertise that a bit for them. So the 3D model, this is at a certain time step. I'm showing 2 parts of the solution, the aperture. So this is that A I talked about. And it's red for positive and blue for small values, and it's growing. I didn't show on this slide the same equations as before for the rock displacement. And then on the right side, let me say the setup for this is that we're injecting fluid along this axis across, and then the aperture is growing radially. I'm injecting at the center. Injecting at the center, and then the fracture is growing radially in sort of a disc shape here. I've cut through the discs to sort of see what's going on. And finally, for this part, we're trying to simulate the advection of this concentration, C, and because of gravity, it's going to settle down at the bottom, but it takes time for it to do that. It depends on the injection rate. And then this geometry was chosen because we can compare some analytical solutions for an idealized geometry just for the fracture opening. And then if we're convinced that that was inaccurate, we have greater confidence in the concentration calculation. I should probably say that there aren't really good benchmarks for this because it's getting into more complicated physics that haven't been studied by so many scientists. But again, the result in this case is just that the concentration has some distribution along the bottom of this crack. More generally, it would just depend on whatever the geometry of the crack was, which would depend on how we initialize it, which might depend on observations. If we're doing a lab experiment, we might have CT scans or something and try to put realistic geometry in. Okay, the rest of this talk is about the part I've been leading myself, is analyzing the actual Joule heating. So it's focused on thermodynamics and then electricity. So I mentioned Joule heating before, I mentioned diffusion before. Joule heating, if you don't know, is proportional to the square of the electric current, which is basically how a toaster works. You put current through the wires of the toaster and it creates heat. So the current is proportional by Ohm's law to the electric field, which is the gradient of the electric potential. Then there's Ampere's law, which because it has a curl of magnetic field, if we take the divergence, we get a non-divergent current. So I take the current from before, and I have to make it non-divergent, and that turns out to be what's called a Laplace equation with a potential. So this is a very well-studied equation when sigma is a constant. When sigma is a positive function, it's a more challenging equation with some solutions known, but not in general, although there's a very good theory for it. So we're going to take a very simple case of just a rectangle to get some analytic solutions. And then we'll have two insulating boundaries. So I'm thinking of like a channel now. So I had that conductive material that's going to provide my conductivity, which I'll mention on the next slide. And then think of that channel of insulating boundaries and then a potential difference W at one end, and then a different potential value, which can be arbitrary because we're only interested in the gradient at the other end. So W is some potential difference across my borehole anode and cathode. So that's one of the physical parameters. That's the one that the operator would have control over. And we'll see how the system responds to it. Okay, so diffusion is proportional to the divergence of heat flux, and that is thought to be proportional to the temperature gradient. So we have a kappa grad T, somewhat similar to the permeability times grad P. Kappa grad T is a flux of temperature instead of flow. So if we keep a simple model of how temperature responds to these processes, then there's the heating, which is the sigma grad V squared. That's the Joule heating, and then the diffusion, and they'll act in opposite directions pretty much. So as you run a current, this is contributing to a positive rate of change, del T by del T. And the diffusion, because you have two derivatives, it's going to sort of tend to get the curvature going the other way and be a negative effect that'll tend to diffuse and move the heat away from wherever it's starting. And those terms compete with each other. We need to keep the unit straight. So the volumetric heat capacity changes the temperature rate into an energy rate. Diffusivity we mentioned, and then we'll have initial and boundary conditions on the temperature, which I need from the next part of the model. So this shows that the electricity couples into the temperature, which I think I've explained the physics of pretty well. We have not yet said that the temperature couples back and affects the electricity. So let's explore that for a moment. Conductivity, sigma, is often believed and shown experimentally to vary with the temperature. And that there's a so-called temperature coefficient, which is the simplest kind of model that sigma depends linearly on the temperature. So when the temperature is at the initial condition or the boundary, I just have some reference sigma 0. But as the temperature departs from that, the conductivity will change. Now, for most materials, alpha is a positive number, so conductivity would decrease as temperature increases. But interestingly, for some materials like carbon and silicon, you can have negative temperature coefficient. And in the Earth, we really don't know. There's reason to think that there's positive or negative values in different situations. So that's something to explore. There's literature out there which claims there's an important effect. So I'm doing a mathematical study in the context that there is evidence to think it's relevant. It may be proved irrelevant someday. That'll be too bad. But we'll see. Okay, so there's a dimensionless number, a unitless number, where I combine the parameters we've been talking about. So the temperature sensitivity, the reference conductivity, the voltage we're applying, and the thermal diffusivity. If you think about the equation on the previous slide and put these together, this number J, the Joule number, is unitless. So it represents the importance of the effects of heating on the numerator relative to diffusion on the denominator. So we're going to do a perturbation analysis. So I have this temperature, I have some initial temperature, and I'm just going to look for a short interval at some perturbation T1, and I multiply it by epsilon. As always, epsilon is a very small number. And then I ask the question, will that small perturbation initially grow or decay? If I consider the variables of the equation, the rate will be proportional to this kappa divided by the x, which is my domain length, squared. That'll be a rate quantity. And then I'm going to linearize the equation. Remember I said it was nonlinear because I have the square of the electric potential. I multiply by let's look at it again. I'm the electric potential, which depends on sigma because it solves this equation. This will be a nonlinear dependence of V on sigma when it's solved. It'll depend linearly on W. Then I take the gradient and square that, so that's nonlinear dependence on sigma. Then I multiply by sigma, and then sigma depends on T. So it's a very nonlinear system. And then we have some fun linearizing it. And we're going to look at the linear system without too much pain. And then the eigenvalues of that linear system will describe the initial growth or not. And that's sort of the key question. If diffusion is dominant, then there will be no growth. If the applied voltage is strong enough, there will be growth. What happens next, we'll conjecture in a moment. Just to have the last bit of math here, not quite the last. I have eigenvalues, I have eigenfunctions of this linear system. I can project the temperature onto the eigenfunction, and that just to show that the dynamics of that projection are just proportional to this eigenvalue. So this is one of the few equations everyone will learn in a math class of differential equations, and it can be solved. And if it's lambda, it's positive, it'll be increasing, and if it's negative, it'll be decreasing. So before I get into more math, we'll divert into the real world with some measurements. This is a plot from a thesis from a while ago titled Dielectric Breakdown Front Propagation. So that's very relevant to what I've been talking about. I have the breakdown is the transformation or damage to the material. Electrolinking is this idea that between two opposite voltages, I can create a path of current, and that would cause damage in the material. They were looking at coal in that thesis, which is, as I mentioned, has that negative alpha. So these are data which I can sort of estimate alpha from. So if I look at a certain range of temperature, then I can roughly calculate alpha to get about 2 per Kelvin. If I look at a different range of temperature, I can do another rough calculation to get negative 0.1 per Kelvin. So these values are just sort of comparable, and One is positive and one is negative. They aren't crazy numbers off the scale. So that's a little bit encouraging. I'll do it again for some other paper. There are many papers like this, and I could make several slides with it. But I just picked this one because it's so intriguing that it's so complicated. So in this paper, they were studying directly the electrical conductivity of granite. Granite, of course, is much more relevant than coal for enhanced geothermal. This paper has a kind of a path because of chemical transformations, which I am not trying to model, but ultimately we should. But again, if I just look at certain intervals of temperature, I can do a rough calculation of alpha, and I get positive 0.1 per Kelvin. Or if I take a different interval of temperature, I get negative 0.2 per Kelvin. So the exercise was just to see that alpha can be positive or negative. Other people have tried to model conductivity as not a linear function, but a nonlinear function of temperature. So then alpha would be a function of temperature, which it clearly is. So there's lots to consider in trying to model this important sensitivity. Okay, so one last bit of math, and then I'll try to tell you what it all means. I'm going to assume that the perturbation is sinusoidal initially, and then I'll use the letter I for the wave number, and then I'm going to non-dimensionalize the equation using this combination of parameters, and then I get this operator, which has a relatively simple form because J is dimensionless. That's our Joule number from before. I is just an integer. Delta Ij is the good old Kronecker delta. And then O has this funny expression, which is vanishes when I is even, because -1 to the I is -1. I'm sorry, +1. And so it cancels when I is even, and when I is odd, it's -1. And I get 4 over pi I. So it's an interesting operator. The first part of this is sort of a screened diffusion operator. And the second part of it is what's causing instability potentially. So there's a nice diagram I came up with. I say it's nice because it's a complicated relationship between the eigenvalues and J, and it was nice to find a way to sort of represent the information on one picture. So in this picture on the abscissa, on the x-axis, I have J, and on the y-axis, I have J minus lambda. And I choose those coordinates because in solving the system, I get a relationship between J on the left-hand side and J minus lambda on the right-hand side. And this converging series converges to a function which is sort of like a tangent function, which is what these red curves are. These red curves are like arctangents separated vertically. The blue curves are half of the eigenvalues, and the other half of the eigenvalues are on these asterisks here, which are the intersections between the red curves and this straight line. So the eigenvalues can be positive or negative. When the eigenvalue is negative, that's up here in the yellow region, and that's the stability. So there cannot be any kind of growth of the temperature. If the temperature doesn't grow, it just diffuses, not much can happen. When the eigenvalue is positive, we're in the unstable region on the other side of the yellow region. And then we have instability, and something could happen given this simplified model. That's enough math, I think. The first half of the eigenfunctions are just the even wave number sinusoids. The second half of the eigenfunctions, okay, last bit of math, is this series. So it's a sort of a Fourier series with these decreasing factors, dividing by these factors as I add terms. And I can make pictures of those. I don't have much to say about them, but it's nice to know that they look reasonable at least. And then the last slide I have is to talk about what this last part really means. So if you remember the definition of the Joule number, there was only one part of that I really had control over. There was the temperature coefficient, the background conductivity, the thermal diffusivity. Those are properties of the formation, and maybe the brine in the formation, or the composition of different things in the formation. Not too much control over that, although I do control the property. So that's important. I don't totally control the distribution of the property. So, you know, there might be some measurements to do to understand that Joule number. But the W I control pretty easily because that's the voltage difference I apply between the boreholes. So in order to have any kind of instability, I need to choose W big enough because W is in the numerator. W squared is in the numerator of that Joule number. We had this result. Oh, it's going to be in this slide, sorry. So W is what I can control. Now the eigenvalues, as I said in the previous slide, will either be in or outside that stable region. So here's the result I was looking for. If J is in this interval, so J is dimensionless, so if it's in this interval, then the conductivity is just not sensitive enough to the temperature. So there's no unstable eigenvalues, no positive eigenvalues, and the temperature will always diffuse. So I'm pretty confident about that. And you know, unless some missing physics is important, but I think I consider the most important physics. But if J is less than this value or greater than that value, there are unstable eigenvalues. Now J is proportional to alpha, and if alpha is negative, then the instability is due to positive temperature increasing the conductivity. There is a regime where alpha is positive and you can have instability due to cooling. I'm not sure how I would start the cooling, but in principle that could happen for a short time before warming probably would take over. But we're interested in the warming case, T1 positive. Now, the last thing to say is we're only considering diffusion and Joule heating. So there could be other thermal, hydromechanical, chemical effects. I don't know if they would be more important, but they might sort of complicate things. So I want to disclose that. Obviously, the growth won't stay unstable. This is a linearized analysis. To really know what would happen, we need to solve the nonlinear equations again. But I do think this result is a minimal necessity for thermal instability. Thank you for your attention. I think we have time for questions.
Thank you for this very interesting work. My understanding is you need this negative alpha to induce instability.
Yep.
Kind of like a thermal electrical kind of a breakdown phenomenon where you sort of localize this heating from. So it's you're saying that as you get hotter, conductivity gets higher, and then get more heating to get like a heat pulse that sort of pass through the system. So my question is, this is just for the rock, but you also mentioned you need this poppant.
Yeah.
So do you actually need the poppant or not to actually have this breakdown?
Thank you for the question. If we had a fracture and we had, say, brine in the fracture, the brine would be more conductive than the granite around it. So maybe without the proppant, something could still be done because the brine would be conductive enough. You know, it would have its own Joule number, and then I would apply the voltage. And if I have some instability due to that, I'd create more fractures. Maybe some more brine would get in. So it's definitely conceivable that I don't need the proppant. Based on past studies that the lead of the project looked at, he thought we should maybe plan to use the proppant because it's like a guarantee or supporting that a highly conductive material. And the proppant can be made very conductive.
What are they?
Coke, whatever that means. It's a kind of a cold product.
And when it's the proppant, they actually burst, like has the volume change upon some critical temperature?
It's grains that are injected, and it's called a proppant because it props open the fracture. So when you inject, the mechanics are elastic and you open the fracture and the fracture will naturally try to close again. But the grains get into the aperture and into the contacts, what do they call, disparities or something? There are, the fracture cannot close, even a small amount of grain will stop the fracture from fully closing. And then if the propant's conductive and the brine is conductive, then you can put a current through there. If you don't have the propant and there's enough residual stress, it'll close the fracture entirely, and you'll basically have, almost a healed granite situation, which is not so conductive.
Okay, it's basically like a solid suspension.
Yeah,
And once you squeeze away the fluid, there's still solid.
that's right.
Yeah, so I think our second speaker is not here, so there's actually questions. Any questions? Yes.
Very interesting talk and talk. I'm just curious, in the real operation, do you do like a traditional hydraulic fracking first and then adding the voltage stuff?
Right. Yeah, I think I said that very briefly, but in this picture, we're showing that we do some traditional fracturing just to get started. I mean, it wouldn't necessarily be this disc shape, but you would need to create a small volume into which you can inject the propant, and then do that quickly enough so that as it closes, the propant prevents it from fully closing, and then do the step with the voltage.
Okay, so that's a further adding voltage will make it this fraction even better.
Right, and you're using much less water because you only need the water you need for the initial injection, not the full fracturing of the whole.
So you're
Like
still
formation.
keeping the voltage, keeping the pressure.
You can stop the pressure. So once the propant is in, you can stop injecting. There will be a natural sort of backflow. There's some engineering questions that I wouldn't pretend I fully understand, but my understanding is that intentionally we don't need to maintain the pressure because the propant will keep the fracture open, and then the electricity is going to replace that work by the injection.
Okay, and then in your simulation, I'm curious, like you have those parameters. For example, you mentioned about the interactions between your fluid and the rock or particles. What kind of interaction, or how did you get that data to define that?
Well, there are properties that, it's a great question because in the field, it would indeed be difficult to know what those should be. So in our project, we have both lab experiments, and then we're relying on field measurements for some properties. In a given field, we may think, oh, the properties here are the same as they were in some other field. That could be a risky assumption. But there are measurements of everything, but there may not be measurements where we need them. So that's definitely something to look out for. I wanted to try to find some of those relationships, but there are definitely properties that are questionable, and you have to estimate them as best you can. I mean, a lot of my career has been working on uncertainty quantification. So I would always give a sponsor a number with a range around it and help them understand what the uncertainty is so that they can make a decision to do or not do something and kind of hedge their bets.
Very interesting, like a project. Just
Thank
maybe
you.
one last question.
Please.
So when you adding voltage, you mentioned like the major contribution is this door heating temperature changes.
Yeah.
So, but you also mentioned you may directly adding the particles, electrical conductive, and based on the fluid. Because when you're adding voltage, you basically will introduce two kinds of mechanisms. Right? You may have the electrochemical driving of those particles, those moving may help. So I'm curious, will that impact this?
Are you thinking of the electricity pushing the particles?
Yeah, kind of voltage, right? Electric
Yep.
migration of those small particles in the system. Because hydraulic fracking, basically will have a mixture of all kinds of particles. So will that contribute to the fraction process too?
Yeah, it's possible that it would. The way the equations are set up now, I'm assuming a Darcy flow, which only has the pressure gradient. But I worked some years ago on what's sometimes called the seismoelectric effect, where there's a electrical forcing in the Darcy flow. It's more generalized, comes from the work of Pride at MIT, actually. So generally, the electric effect on the fluid itself is pretty weak. Now, on conducting particles in the fluid, it may not be so weak. So I'm going to take your question back to the people doing that part of the simulation and see what they think, because I think it's worth considering. If I think what their answer is going to be is that because the fracture is closing up again, those particles will be under sort of a transverse confining stress. It will take the voltage won't move them that much. But if that's incorrect, if some of the proppant is holding the fracture open and other proppant is kind of free to move, then indeed that voltage might push that proppant away. Or pull it the other way. I'm not sure what happened. Well, thanks for that suggestion.
That impact may be mirror, I'm not sure, depending on the size of those small particles.
That's right. Thanks for the suggestion.
Other questions?
This was an interesting talk. I just wanted to ask, earlier you said that the initial fracture that you modeled didn't have any specific shape or geometrical properties to it. And then you also said that you hadn't really considered any mechanical properties in this process, you just focused on the thermal. I was wondering, do you believe that a specific fracture shape would lead to easier fracture, or do you think that probably fracture not situation?
So my understanding from others' work is that for the hydraulic fracturing, a given formation will have directions intrinsically which are favorable for the fractures to propagate. And that's the state of affairs when you introduce the hydraulic fracturing, the pressure. It's very difficult to predict where those fractures will be. You try to engineer the system so you don't really care too much. Once you have like a main fracture, hopefully intersecting the boreholes you have to put the voltage in, then I think the geometry probably isn't going to be so important, because the idea is that with the proppant connecting the electrodes and cathodes, pretty much that lightning strike in the early slide is going to create lots of small fractures. Ultimately, what I want for enhanced geothermal is that cold water can come down and circulate through a lot of hot rock and come back up and run turbines. So the details don't matter so much. I don't have much control over the initial fracture, because that depends on the formation, but I have like seismic surveys and different kinds of surveys giving me some idea of that. But then once the fracturing is done, and the electrical fracturing, if it's efficient and creates lots of small fractures, then I don't care too much about those details. Thank you. Excuse me.
So can you give us some idea of how high the voltage is, and then what kind of length scale are we talking about?
Oh, I hate this question. You see, my talk is all symbols. So I'm an applied mathematician, and I should go out and get some real numbers. I'm so sorry. We'd have to take like actual numbers, which I've only done a few of here for the alpha. But I said that the growth or decay rate was proportional to the diffusivity over this sort of dimension I'm calculating. So if I imagine there was, a rectangle, a channel between two boreholes of say 10 meters, then I'd be dividing by 100 meters. I don't know what the diffusivity is here, but that would give me a growth rate. The eigenvalues, lambda, we can read them off in these charts. So there are numbers like, this is growth rate. So, they're not very large numbers. So 10 over 100 is like 1 over 10. But I didn't look up a diffusivity. So the diffusivity is sort of the controlling thing. The larger the diffusivity, the slower things will happen.
But it's like through 10,000 volt or something
No, faster things will happen.
like high voltage across.
Well, yeah, we're envisioning pretty large voltage because probably the range, 1,000 to 10,000 volts are the kind of numbers I've been hearing. The purpose of my study was to try to make that efficient, to say, how do we tune in that to what the actual properties are? I think in practice, you build the system to deliver some range of voltage that you can afford that you think will be sufficient. That's actually like the last few deliveries of the project, is to provide a guideline for operators to say, this is what you should design to create. I'm sort of the preliminary part of that. I think it's a very good question to ask. I still like trying to answer.
Yeah, one last question is you showed this Biot effect. Could you explain a bit? Because I see that effect is appearing both for the fluid part and for the solid part.
Yeah. Yeah, so Biot has a very beautiful and complicated theory. It's rewarding but slow to read his papers.
Because there's this alpha which appears on both places.
That's right, and notice that the alpha multiplies the strain, which includes the gradient, and then on this side.
So sorry, that strain rate is the rock, or that's not the fluid, that's the rock strain.
Correct.
Yes. Yes. When the rock is expanding, sort of squeeze the liquid, it's like a source comes to the liquid.
Exactly. Yeah, that's what that represents. And then this sigma minus alpha p is what's so-called the effective stress. So if you had no fluid, the continuum would have some stress field, but when you have a fluid, then there's some, if the pressure is positive and alpha is positive, then there's a reduction in the stress because of the presence of the fluid. There are different, if you look up effective stress, there are different kinds of pictures of trying to give the idea of sort of the fluid is occupying the void around stress, and it has the effect of reducing the stress, which is why it's subtracted here. I'm not very good at explaining it because it took me a long time to learn it too, but this is the effective stress concept, and it is very well confirmed in experiments that there's a slowdown in the velocity. If you calculate the velocity like waves moving through the medium, it's the effective stress appearing here that controls that velocity.
Thank you. Other question? Oh, and thank you, Aimé, for this great talk. The second speaker is not here, so we'll move on to the third speaker. Fourth speaker is
What time is it now?
I think both number 200 and 249 on here. 257. That's 90, 200, 249, and 257. Hmm? 62.
Are any of the four talks before 10:25? Are any of those speakers here yet?
262.
262 now.
10:45. Yeah. I mean, in a way, it's unfair to go too soon because people might come.
Sure.
But is no one, are none of 41 or 200 or 249 or 57 here? I mean, it's maybe it's too soon, but 9:05, we thought they would not come. 9:25, it should be coming right now. Brooke, Yuyin, Bang.
Well, if you're not here, then you have to do, so you can stay in the room or, talk, but I think, we just, generally, thank you.
Yeah, I think, I agree. We should definitely go check in at 9:45. And